This geometric cluster represents the core of Discovery Intelligence, a system designed for long-term scientific decisions and discovery. The system manages a deepening hierarchy of structured objects, like canonical scientific states, detailed run metadata, new experiment requests, and core belief updates. As these layers multiply, a human researcher must be able to identify what is unresolved, inspect what changed, and retrieve specific candidates of record. The difficulty of navigating these objects grows faster than the machine's ability to compute them. This schematic illustrates the clash between natural language and a rigid database. Human intent is variable and unstructured. When a user asks a nuanced question, the request often fails to map cleanly onto the specific grid-like requirements of the core tables. Advancing a scientific architecture requires solving these interaction constraints with the same mathematical rigor applied to the data itself. We are exploring Gemma models as a bounded interaction membrane wrapping the scientific core. It acts as a bridge, permitted to read, retrieve, route, and explain data. However, it is strictly walled off. It cannot determine scientific truth, rank candidates, or rewrite canonical evidence. This design ensures that probabilistic AI remains secondary to deterministic scientific processes. A physical architectural boundary is a more reliable safeguard than prompt engineering to prevent data corruption. Selecting the right model for this membrane is a strategic engineering decision. Gemma is classified as an open-weight model family. This compares closed API against open-weight architecture. On the left, frontier models operate in a remote, black box cloud. On the right, Gemma offers a different path. Open-weight means trained parameters are available. We can download, host locally, and integrate it directly into our secure environment. Relying on a remote API for a central interaction layer introduces long-term risks. If the remote service changes or a black box update alters the model's behavior, the stability of the entire interaction layer is compromised. Direct control over the weights ensures the model remains predictable and stable over the lifespan of the Discovery Intelligence system. For this integration, architectural control and bounded adaptation are more valuable than raw generative capability. The first functional layer of this membrane uses embedding Gemma, a specific model for mathematical retrieval. This visualizes a high-dimensional space. Embedding models process text objects, like experiment logs, converting them into numerical coordinates. By plotting text this way, the system calculates semantic similarity based on physical proximity. Related concepts map to coordinates sitting close together. This allows a user to locate information by meaning rather than exact keyword matches. A researcher can locate runs with similar bridge state characteristics simply by retrieving data points within a specific spatial cluster. Mapping these documents mathematically is a retrieval task, not a reasoning task. The AI is identifying patterns of proximity, not evaluating the validity of the science. Turning unstructured intent into mathematical coordinates resolves the retrieval friction without giving the model authority over the data. The second integration layer is function calling. It is important to clarify that function calling does not grant the model independent agency. It cannot execute code on its own. Here, the model interprets a natural language request, converting it into a structured JSON block. This block acts as a secure transport, crossing the boundary to trigger a deterministic function inside the core. The core computes independently, returning raw data for Gemma to format. Function calling is a routing mechanism. It ensures our deterministic scientific tools remain the sole authority, untouched by the model's probabilistic logic. The final stage of this architecture is fine-tuning. Fine-tuning is the process of adapting a model's parameters so its behavior aligns with a specific, narrower task. To manage compute requirements, we use parameter-efficient fine-tuning. The massive base weights of the network are frozen, while a smaller secondary adapter layer attaches alongside. Only this adapter updates with new data, specializing the model's behavior without the overhead of retraining the entire network. We use this process to train the model on Discovery Intelligence terminology, core object vocabulary, and bespoke tool schemas. We are tuning the model for obedience and structured routing. We are not tuning it to generate scientific conclusions. Fine-tuning allows an organization to bake behavioral compliance directly into the network architecture. This is the integrated architecture in motion. A user query hits the translucent interaction layer, routing through structured pathways into the protected core. The architecture maintains a clear duality, a membrane to handle the ambiguity of human intent, and a core to handle deterministic logic. By combining embeddings, secure function routing, and tuned adapters, the system provides a seamless interface without compromising the safety of the scientific data. In a high-stakes scientific environment, the predictability of the interaction layer is a primary design requirement. The generative model remains walled off from the canonical scientific truth. Discovery intelligence computes the science. Gemma exists to help humans interact with it.